Hello to everybody. Thanks for joining today's webinar. My name is Harald Pieringer. I'm a founder and the CEO of Visplore, and it's a very big pleasure for me to host this webinar today. Today's topics is physics-based modeling of power plants. So it's a very great pleasure for me to welcome Mr. Petek and Mr. Pölzl from ENEXSA. ENEXSA, in brief, is a company for expert consultancy and software systems for the power industry. They have been using Visplore for the project for more than 2 years, and I'm very happy that they will give us insights today about their work and where in the project scope Visplore comes into play. After their talk, I will add a few words to reflect about the process of building digital twins in a bit more general way. And in the end, you are very much invited to ask questions to ENEXSA or to myself. For this, please feel free to type questions in the chat anytime, also during the talk. We will address them in the end. Now, without further ado, I hand over the word to ENEXSA, and I'm very much excited to hear what they can tell us. So please, Mr. Petek, the virtual stage is yours.
Thank you very much, Harald. Good morning or good afternoon, ladies and gentlemen. Let me start my presentation. Visual data analytics for physics-based modeling of power plants, our cooperation with Visplore. We are working with the Visplore tool since, as Harald mentioned, 2 years now, and we have grown into that field. First, let me ask for allowance to tell you a little bit about ENEXSA and give you an introduction to our company. ENEXSA is actually an abbreviation for Energy Expert Software Application, and this short name comprises very well what we are doing. We are delivering expert consultancy and software systems for the power industry. Some of you may already know our company under our old name, V2 Energy. Since the year 2019, we have renamed the company to ENEXSA as the core team of the company acquired the ownership through a management buyout. We are currently a team of 21 persons, as you can see on this picture, quite nice looking young ladies and gentlemen. What is our portfolio? Consulting and thermodynamic simulation. Based on thermodynamic simulation, fuel demand models and settlement systems for independent power plants and independent water plants. Plant simulation models, and this is what I will give you more detail in today's presentation for a specific application of a simulation model for performance monitoring. We are co-developing the Epsilon Professional Heat Balance software that is owned and licensed by STEAG Energy Services of Germany, but ENEXSA since many years works with STEAG to improve the software, to extend the capabilities of the software. And we are also offering complete turnkey optimization systems. The range of our knowledge, know-how, and tools covers the entire power generation portfolio. Like you can see on the slide here, upper left, a combined power and water plant in the Middle East, where a gas turbine combined cycle power plant produces power, and part of that power is used to run reverse osmosis desalination units for seawater desalination. Upper right is a special application of a heat recovery boiler connected to a compressor station of a gas pipeline. Lower left is a combined is a concentrated solar parabolic trough power plant, the Shams 1 power plant in the Middle East, the very first solar power plant in the Middle East. Meanwhile, we've worked also on other types of solar plants. And lower right shows an electrolyzer unit, as of course in the era of Energiewende, We are expanding our portfolio to renewable applications like solar, wind, but also storage, batteries, and electrolyzers, as shown on this picture. But behind of all our work in almost all of our projects is the thermodynamic simulation, and the tool that we are using for this purpose is the Epsilon Professional Heat Balance software by STEAG. As you can see, the plants are modeled from unit operations, individual heat exchangers, the gas turbines, the cooling towers, individual sections of the steam turbine, or photovoltaic cells, the wind turbines. Everything can be put together into a system, and it's a system-wide approach that can be taken using this software. Our projects and customers are spread worldwide, from the west coast of the US to Japan. Big names like big gas turbine manufacturers, Mitsubishi Power, GE, Ansaldo, they use our heat balance software. We have utilities like NextEra Energy, Florida Power and Light, STEAG using our software. And we have in the consulting, for instance, OMV of Austria or the voestalpine steel mills of Austria as customers for our software tools. You can see a very dense location of projects in on the Arabian Peninsula. This is our specific portfolio of fuel demand models and settlement systems, where we apply our know-how and simulation skills for long-term power and water purchase agreements and respective performance guarantees related to that. Big names in the energy business like Engie, Marubeni, Sumitomo, Sembcorp, Aquapower are our customers in that field. But with that, let me move to the topic of our presentation of today, performance monitoring and visual data analytics related to that. First, an introduction to performance monitoring. You have in a power plant, you have the individual equipment, and if you want to do condition-based maintenance, you certainly want to see at which location of the plant there is performance gaps, there is performance degradation caused by fouling or erosion or leakage. And this can be done by comparing the measurement of the plant, the current status of the plant process, with a process model, a physical model. It's a first principle model. Mass and energy balances are calculated for the current operating point to see deviations between the expected performance from the model, the benchmark model, with the current measurements. And this can then be transferred into performance information that is fed back to the plant historian to produce trend lines of key performance indicators, efficiencies, temperatures, mass flows of the power plant, so that specific problem areas can be detected and condition-based maintenance can be applied. Now, how can you locate the performance gap when you look at measurements? You have a current condition, in this case, as an example, ambient temperature against a KPI, for instance, gas turbine generator output. The current operating point gives you X megawatt at current Y degrees centigrade. You know from your performance test or from guarantee numbers of your power plant that you have a certain reference state at different ambient conditions, different other operating conditions. So how can you now find out what is the current performance gap of this gas turbine? For that, you need a model that depicts that correctly describes the performance characteristics, how power output changes with ambient temperature, for example. So from your reference point, you can then calculate under current conditions what is the expected output of the gas turbine, and with that you have a performance gap identified. This performance gap can now be transferred back to reference conditions, because what you want to see in a trend line over time is performance at a comparable state, so at comparable conditions, reference conditions, and at the same load level, because efficiencies, of course, change with the load level of the power plant. So this corrected parameter, corrected power output, corrected flows, corrected pressures, they can be compared over time and can be then the trigger of the KPI alarm if there is degradation, if degradation is exceeding the allowed ranges. How do we develop the performance characteristics? We start with vendor information. So with the plant documentation, there is vendor heat balances that describe the equipment at different operating conditions, not only a single baseload or guarantee point. We of course need performance characteristics at different load levels so that we can compare the individual equipment performance and the equipment data and adjust the model to exactly match those data. On the right-hand side of this slide, you see a scatter plot that compares vendor heat balance data with model results after tuning to those vendor data, and it shows a perfect match. So the entire operating range as per the vendor data is well met. Trending the KPI over time is shown here. So the green line in this left side graph shows the sequence of operating points as measured. And the red dots give the expected value for the current condition. So every operating point, in total it is more than 400 in this graph, is an individual operating point, a steady state operating point in which we can compare measured to expected performance. There is an up and down, there is changes here and there. So how can you trend that over time? This is then the blue line. The blue line in this graph is the corrected parameter. And here you can see up to a data point 140, the corrected parameter, in this case it is a steam flow from an HRSG, is fairly constant. Yeah, there is of course a little scatter with in this harsh environment, and with the measurement accuracy you have a certain scatter. But after this 0.140 you see a drop. This is some performance problem that can be detected here in this line. And on the right hand side you see a scatter plot that also shows that over the entire range of operating conditions, there's actually a mismatch between the measured data and the expected data. The expected data show a slightly higher value over the entire operating range. This now is a clear indication that performance degradation has occurred, and the benefit for the plant is that they can look at this issue either if there is any leakage in the plant in this HRSG, or if there's other problems, and they can prepare for maintenance actions much more effectively, as they're already aware of where to look when there is a shutdown of the plant. So what's the problem in the whole process? Well, as explained, this way of correcting from current operating point to reference conditions requires that you have a correct performance characteristic. And because the performance characteristic depicts the natural behavior of the plant. So if temperature changes, by nature, the output changes. There's higher mass flow through the turbine, so output will increase. These changes must be correctly modeled so that the KPI does not depend on the load level or on ambient conditions. So our models must be refined to really depict the correct performance characteristic. Now, the performance characteristic that we receive from the vendor are only a few operating points, a few heat balances. So we must look at more operating conditions. We must find operating conditions to tune our models to. And second, the vendor data also commercially include margins. So the plant as built may perform a slightly different, more or less, but slightly different. So this also needs to be tuned in the model to really reflect the plant as built. So the task is to look at measured data from the historian of the plant and select data that can be used for model tuning. And this is where Visplore comes into play. We have to collect data that are clearly steady state, because transient conditions do not match heat and mass imbalances. And second, we need to select clear defined operating conditions that we can then apply to the models. Visplore is the perfect tool for us for this purpose. And second, once we have tuned our models, we can go back, load those data also to Visplore and allow to verify our model quality. And to demonstrate our work with Visplore, I would like to now hand over to my colleague Martin Pölzl to give you the demonstration of the application. So, Martin, please come in.
Thank you, Joseph. In today's meeting, I would like to walk you through an example of looking to analyze gas turbine operating data, and we are going to compare those data with the thermodynamical model results that we have prepared. And do that, of course, using Visplore. I'll walk you through a 3-step process. We are going to start with selecting particular operating conditions out of a raw data set that we receive from the customers. Once those data are selected, we run those data sets through our mass and heat balance software tools that we have generated, set up. And as a third step, once we have the results from those model executions, we come back to Visplore for the evaluation and analysis of results. So we start with opening the raw data file. This raw data file contains about 7,500 data records. And we load these data records into a trends and distributions platform of Visplore. And what I do first here is I switch from the actual measured timeline to an arbitrary timeline, which I have introduced just in order to get rid of extended data gaps that we are faced with in this data set, to make it easier to look at trends over time without looking at the data gaps in Visplore. So once the cockpit has loaded, we will start selecting appropriate data sets. Our target in this example is to look at full load data. The full load information of a gas turbine is something that is provided by the engine's control system through a base load indicator, and this base load indication is also part of our data set. So I'm looking for this indicator parameter. And what we do next is we want to select all data sets where this indicator parameter shows a value of 1, indicating full load. Visplore offers some graphical selection methods to do that. It also offers a method of generating what they call a condition. There is a conditions dialog, which allows for a script-based simple calculation definition. So I need to do some simple scripting here, identifying that my parameter value must be greater than 0. Once I confirm my input, click OK here, Visplore is going to generate a named condition, and this named condition would now be available for filtering options. So I put this condition into what Visplore calls the focus. And what happens is that all data points that show a value of 1 are now active, and that reduces the amount of data from 7,500 to around 4,000 selected data points right now. That is still a quite high number, provided that it takes some time to execute the thermodynamical models. So for a first quick check, it might be advisable to further reduce the amount of data. And in the example here, I do that by adding another time-based filter criteria. So I select the data points of every 10 seconds, add that to the focus, which results in a remaining a data set of 411. So with that, we are now able to, or prepared to export the 411 data sets. So I use the filter option here. I put what they call the focus to the filter, which essentially removes the non-selected data points. And for data export, there is several options which Visplore offers here. We are going to use the option to export the data to the clipboard. And this is because our tools that further process the data, that call the thermodynamical model, are either set up in Excel or they are set up in Python. And what Visplore provides here is an identification parameter. Instead of exporting the full set of data, we just export this identification parameter. And when I open my Excel template here, there is a specific place where I need to place this exported selection information. And from here, we have generated some VBA-based macros that would allow to import the corresponding data sets in the specific format that is required to communicate with the Epsilon software. And once that is done, we are ready to execute these data. So we call Epsilon also through some embedded Excel add-ins. And once model execution is finished, Epsilon returns the results back to Excel. And then we use another VBA macro to generate a results CSV file. And now we can start with step number 3, importing those model calculated results back into Visplore for further results analysis. So again, we open up, in this case, the results file. We use the trends and distributions cockpit. And while opening the cockpit, we'd have to go through the same process of adjusting the time reference. And once the cockpit has opened, we can already start with looking for data analysis. I would like to focus on the some of the KPIs of the gas turbine, namely the power-related KPIs. So from the list of parameters, I pick the corrected power output, the expected power output, like expected, second line here, and also the actual power output. In order to verify the models, it makes sense to put independent parameters as well. what are the independent parameters for a gas turbine full load situation? The most impacting parameter would be the set of ambient conditions, and out of the ambient conditions, the temperature has the most impact. So therefore, I add inlet temperature as well. And now I have my parameter set prepared to start with data analysis, and I do that using a set of scatter plots. We trend, or we generate scatter plots where we put the KPIs over independent parameters. What we see here is the corrected power output. Corrected power output, as mentioned before, is expected to be independent on ambient temperature, which is the case for the majority of data points here, but there are some data points that fall off this constant expected number. So we look further. So the next KPI we see here is the expected power output, which is the direct model result. Expected shows a quite clear correlation to ambient temperature, and this is the actual power. Again, we see correlation for the majority of data points, but some data points that fall off the expected behavior. So to analyze the reason for the data situation that we have here, we use Visplore's graphical selection tools, and we try to identify as many of those problematic data points as possible. And once we made that selection, the target is to find other parameters that would help us explain the reason for the situation we see here. Other parameters related to gas turbine operation, one that quickly comes to mind is the gas turbine fuel flow. So I select gas turbine fuel flow here, and in essence I do the same. I plot fuel flow, this time against inlet temperature, and what we see is a very similar behavior compared to what we saw before on the power, which basically proves that we have a systematic problem here. It's not just a problem of one single power measurement. So we dig in further, and one parameter to look at next would be the so-called IGV angle. The IGV angle is very much related to the control system of the gas turbine. For full load operation, the IGV angle is expected to be at full open position. So to double check, we again generate a graph. And if we look for power output over IGV angle, then unexpectedly, we see that there is not just one full open position here. Actually, there are 3 levels of IGVs, and those 3 levels also correlate with power. So we kind of probably have found the reason for the data situation that we see here. And in order to prove that the IGV is the reason for the outsticking data points, we redo the selection now based on IGV angle. And Visplore also offers for each focus configuration to create a named condition similar to the named condition we created based on the script earlier. So I give it a name. Once the name is available, I can reload the condition. And with that setting, I would now like to revisit the trends that we saw before based on ambient temperature, just to verify that selecting this IGV is going to prove that all the problematic data points are affected by the IGV setting. And as you can see here, this is the case for the fuel flow. It is also the case for the actual power output. And finally, it's also proven if we look at the corrected power output. So in this case, with the help of Visplore, we have been able to identify that this particular engine offers multiple baseload selection modes in its control system, each assigned with a different max position for this IGV angle. And the conclusion for our model was that we had to include the IGV position in addition to the baseload feedback that we have added from the control system, just to make sure that our model can mimic the real engine operation satisfactorily. So thank you very much. And I would like to return to Harald.
Thank you very much for this great and informative presentation, Mr. Petek and Mr. Pölzl. I'm already very much looking forward to the Q&A part of the webinar. But before we come to this, I want to take the opportunity and add a few words from my side. So what we have just seen is a practical example of what is nowadays often called a digital twin. This is a hot topic as it offers great opportunities for process optimization and monitoring. As we heard, this was also the motivation in the project described by ENEXSA. Now, this starts actually in the design phase, when it's about understanding and preparing historic data from process historians of the system that is to be modeled. For example, selecting the right data has a crucial impact on the quality of the model. Now, once the model is built, ENEXSA just showed us how important it is to validate it deeply in order to make sure it really matches the behavior of the physical system across all of its operating ranges, and adapt the model if necessary. So, for example, when we find out that we have multiple modalities, it's important to consider this in the model. And when a model has gone operational, it typically generates data that, in many cases, subject matter experts will, in one way or the other, need to consider in their daily work. And finally, sooner or later, the model is very likely to become outdated, for example, due to modifications made to the assets or simply wear over time. It's important to recognize that in time and eventually re-enter the design phase again. And in all these stages, costs due to human effort of working with massive data is where much of the costs and practical challenges are in building digital twins. So what can be done to address these challenges? This is actually where Visplore here, as we have seen, comes into play. Visplore supports the process of building digital twins along multiple stages. First, by cleansing, selecting, and labeling the raw historic data from the assets. This step was one of the focus in ENEXSA's presentation. The concrete result is simply useful data. Labeled data, selected data, filtered data, removed outliers, and so on. This is an essential basis for the entire project. The benefits of Visplore here are to reduce the costs and the project duration by shortening this sometimes very tedious phase. Maybe it's also important to mention that we have seen in the ENEXSA presentation the interplay to get data, for example, to Excel. It's important to mention that Visplore is well integrated with workflows in Python, MATLAB, and R, where it's easy to share data between these tools and work side by side. Second, by making a deep validation of models easy. So, for example, Visplore can show you very clearly at which condition the model output matches the measured data and when this is not the case. The benefit is, on one hand, that this information is useful to increase the quality of the model, but it also increases the trust, as the behavior of the model has become much more transparent. And last but not least, building and using models is much about communicating the results of their data. And for this, we're just about to release a new Visplore version this July that makes it straightforward to build interactive reports directly in the tool. These reports can then be shared with everybody, also without license. And the reports are structured a bit similar like a PowerPoint presentation, but the graphics and the data is interactive so that viewers can still zoom in, change filters, and so on. And this enhances the communication and makes results more reproducible. Okay, so that's it from my side. Thank you all very much for attending this webinar. I hope it was informative. Now I invite you to stay a bit longer for the questions and answers session. Please don't hesitate to ask every question that comes to your mind to ENEXSA or to me. We'll do our best to answer them. And if you don't have time, to answer all questions, we'll back to you and answer the questions via mail. Of course, you're also very much invited to contact us directly. So here on the left-hand side, you see the contact information. So if you have some more questions, please don't hesitate to approach us. So now the stage is yours, and I'm already looking forward to seeing if first questions have arrived. Okay, just a second. Okay, so here is the first question. I think this goes to you. How long did it take you to learn Visplore? I think this goes to ENEXSA.
Well, yeah, Visplore is a quite straightforward tool. It's very intuitive, and it takes within a couple of hours. I was able to, use first dashboards and generate some graphs, doing some analysis with the data. Of course, there is more complex and less complex platforms available, but Visplore also offers a step-by-step introduction and explanation of many topics through its web-based help functionality.
Okay. So another question. Which data sizes do you typically see in projects around digital twins? I think this is also to you, to ENEXSA.
Yeah, I mean, the amount of data that we process, the example we went through is quite representative, I would say. Amount of data range from a couple thousand to like 10 or 20,000 data points. And yeah, that can be easily processed in Visplore.
Okay, thank you. There is another question. Why don't you do the data preparation in Python?
Well, we work with Python as well, but for these purposes, Visplore is just much easier to use. There is no scripting requirement, no coding. It's just opening the software, then the dashboards are prepared. You just load the data and you look at the trends. So for the purpose of our work, it turned out that it's easier to use Visplore compared to Python.
Okay. So maybe I may add to this that lots of our users are actually using Python in a side-by-side manner with Visplore, where they basically use Visplore for things that need interactivity, like labeling data or exploring data and getting a quick sense of what the data does. And for things that can easily be automated and scripted, then of course Python is just excellent. Okay, so one more question. What experiences do you have with data quality in your projects? And is this a problem?
Well, data quality is always a problem. And that's the actual reason why we are looking for tools like Visplore, to identify the problematic areas, to identify the data sets that we don't want to use for our models. So that is the core purpose of the whole thing here.
Okay. One more question. How long does a typical project for building a digital twin take? What's the typical range for that?
Well, that depends on the application, but that can go from a couple of weeks to a couple of months. So for like a performance monitoring project, for a full power plant, we would work for 4 to 6 months in order to finalize everything. For a digital twin of a single unit, that can be done in a couple of weeks.
Mm-hmm. Okay.
If I may add to that, the big difference is working out of window data, heat balances, which are clean data. That's simple. But the moment that you have to touch measured data, and the moment that we start our modeling, actually we can explain to our customers that there is discrepancies in that data, that it's not possible because of the laws of nature that certain measured data coexist. There is simply a lot of conflict in measurements, and they only pop up once you start to do the modeling.
Okay. So there is another question. Can you comment on degradation tracking once the model is built?
Yes, certainly. The KPI lines that I was showing in my slide, this is the indicator. Yeah, and of course they show some scatter. So, and there may be outliers that affect those numbers. So the degradation certainly needs to be lines or trains need to be evaluated either by statistical process control or, as they are lines, by visual. If you look at it, a single deviation should not trigger an alarm, but if there is a clear trend and a clear deviation over time, then certainly you can trigger an alarm. And from the trend lines, you also see the rate of degradation. So by nature, there is degradation from fouling, there is dust that accumulates, there's erosion with the equipment. So there is always some change in or some slope with the degradation lines, with the KPI lines. But the moment that they become too steep, or the moment there is a step, that should trigger an alarm, and that can be automated as well.
Mm-hmm. There is another bit technical question. So which technology do you use then to deploy your models?
Well, it is the Epsilon Professional Heat Balance software that is executed. It's running on a Windows operating system on a server. And we have a link to the plant historian, to the plant database. We read the data, the measured data into our system, process the data, and write back the results. But the Epsilon Professional Heat Balance software is the core calculation engine to our technology. We also have some in-house tools to manage the data processing, pre-processing and post-processing of the results.
Mm-hmm. Thank you. Okay, I think we are almost we've already reached the end of the 45 minutes for this webinar. There are a couple of more questions here in the list. Be sure we answer all of them. We will write those who have asked the questions response emails. And if some more question comes to your mind, please don't hesitate to contact ENEXSA or us. And we will also make sure we will put this webinar online. So we'll do this rather soon so that you can, if you found this interesting, and you can share the link and maybe also show it to colleagues. Okay, finally, I want to thank everyone who attended until now. I want to say one more thank you to you, Mr. Petek and Mr. Pölzl, for basically doing this webinar, as I was here more or less only the host, for sharing the insights about your work on building physics-based simulation models and where Visplore comes into play. And I hope it was great. I wish all of you a very pleasant summer, and I hope it would be great if you found this interesting, maybe to register for our webinar, to have a look at the webpage. We have there several use cases also regarding the energy sector. And also, if you found this interesting, to get in touch with ENEXSA or us to tell you a bit more about Visplore, or of course, to ENEXSA for physics-based modeling. Thank you and goodbye.
Goodbye.
Bye.